All right, so we need to start chapter 7, which is about being able to predict trends using the relative location on the periodic table. So basically periodic properties of elements based off where they are on the periodic table. There's a few different trends that we need to look at. The very first one is atomic radii. Radii is plural for radius. Basically, it's the distance between the nucleus and the edge of the atom. Okay. So you have the nucleus. It's essentially, how far is it from here to here? It's essentially a measure of how big the atom is the easiest way to do it. The problem is that radius is actually really difficult to measure. If you have things that are covalent bonds, which we really haven't talked about yet, things with nonmetals, it measures a little differently than if you have just metals. We're mostly just going to kind of look at general trends here. Okay, so I'm not honestly worried about all the gory details of how this is measured. We're just looking for what is the general trend. Okay, so on the periodic table, things tend to get bigger as you go down, like down within a row, or to the left. Okay, so basically francium is huge and fluorine is really, really small. Okay, so on the periodic table, it increases down and left. Now, that seems like a really easy trend. Great. We need to talk about why that is. Okay, and it turns out that the up and down trend is different than the left and right trend. So let's talk about the up and down trend first. In the last chapter, we talked about atoms and what the shapes of the orbitals were, and we said that essentially, no matter which type of orbital you have, whether it's S or P or D or F, if you have the multiple orientations, like a d orbital has 5 possible shapes, those 5 shapes should come together and essentially make a hollow sphere. So the lowest energy should be like 1s, 2s, 2p, 3s, 3p, 3d, 4s. So basically they get bigger as you add more electrons. So that's literally the trend. Basically, for the up and down trend, more electrons equals bigger atom. Nice and straightforward, really obvious, really straightforward and easy. Great. Okay, so that one's not bad at all. The left and right trend is based on something called effective nuclear charge. So I really need to teach, a lot of what we're doing right now is I need to teach you what that is and how that affects things. Okay. Effective nuclear charge is abbreviated as Z sub EFF. It's called nuclear charge. It's going to be positive because the nucleus has all the protons in it. Z was the atomic number, the symbol we used for atomic number way back in like chapter 2. It's essentially how many protons there are. Okay. So the idea is in atoms there are valence electrons and core electrons. Okay. Core electrons are the innermost electrons. And they end up shielding the outermost electrons from the nucleus. So, and they shield the outermost electrons from the nucleus. Okay. Valence electrons are the outside electrons, the outermost electrons. And basically, they don't provide any shielding at all. Okay, so let's kind of look at an example. Okay, so if we compared something like sodium and magnesium, I don't typically draw these as pictures, but I'm going to just for visualization's sake. Okay. Sodium has 11 protons and 11 electrons. Element 11 on the periodic table. So it doesn't have a charge, it has 11 protons, 11 electrons. So its nucleus is plus 11. Okay. And if you work through the electron configuration, it's 1s2, 2s2, 2p6, 3s1. The core electrons are essentially, for the most part, the previous noble gas. Okay, so it has 1s2, 2s2, 2p6 as the core electrons. Okay, and then on the outside, it has one electron, the valence electrons, that is a 3s1. Sorry, the handwriting's a little floppy there. 3s1. Okay, so this is the valence electron. The idea is that there are 10 electrons here, and the core ones essentially cancel out the effect of 10 of the neutrons. Or sorry, 10 of the protons. So this is 10 electrons, 2 plus 2 plus 6, or it's essentially a neon core, 10. Okay. So what this means is this outermost electron, the one that's determining the size, because it's the one that's farthest away from the center, basically feels a pull of +1 from the nucleus, because the 10 core electrons cancel out 10 protons. Okay, so in other words, how hard this is pulled in towards the center, how much force it has pulling it inward, is only a pull of +1. Its effective nuclear charge is +1. Okay. Magnesium is really similar. It's the next element over. So sodium, magnesium. Magnesium is element 12. So it has a core, or it has a nucleus with +12 in the middle. It also has a neon core, which I'm actually just going to abbreviate as neon, and this is essentially 10 electrons. And then it has 2 electrons on the outside. I drew it bigger. That doesn't necessarily mean it's bigger. I just can't draw. Sorry. So the 3s2 is on the outside. So these are the core electrons. These are the valence. Okay. And then the idea is this core, these 10 electrons, cancel out 10 of the protons in the middle. So these electrons, even though there's 2 of them, don't cancel anything out. They feel a pull of +2 from the nucleus. Because, same reasoning actually, basically because 10 core electrons cancel out 10 protons. So there is since 10 of these are being canceled out, there's a pull of +2 in the middle. So the effective nuclear charge is +2. So even though there are more electrons in magnesium, they are feeling more of a pull, and positive is attracted to negative and actually contracts the entire molecule, or the entire atom, sorry. And so essentially as we go to the right, the left and right trend, okay, is based has almost nothing to do with how many electrons there are. It has more to do with, as you go to the right, the number of protons is increasing on the periodic table. And the number of shielding electrons, the number of core electrons, is not going up. So what's happening is basically as you go to the right, there's more and more positive in the middle, so even though you're adding more electrons, they're being pulled in tighter and tighter. So things get smaller as you go to the right. Okay, so I really probably shouldn't start that on a new page. I'll just squeeze it up here. So for here, more protons equals smaller atom, at least within the left and right trend. Okay, and the effect is based on something called effective nuclear charge. Okay. All right. It turns out, as you might expect from the last chapter, that anytime we have a rule, the D block messes it up. So that's what's about to happen. It turns out that d orbitals, they mostly shield the nucleus. So what that means for us is basically the effective nuclear charge doesn't really change much. We count them as core electrons. They're not core electrons, but as far as the effective nuclear charge side of things, they count like core electrons. So, for example, iron is argon 4s2, 3d6. Okay. Basically, these are core electrons. They're not really core electrons, but we are going to count them as such. I'm going to put a little asterisk by it because they're sort of core electrons. These are the only valence electrons. So basically the only ones that aren't canceling out protons are these two. So the effective nuclear charge is +2. Okay. And it turns out that, I actually have the number over here, the actual size of this atom is 124 picometers. Okay, that's how big an iron atom is. Okay, or that's how big its atomic radius is. But if we compare this to something like cobalt, which is the next element over, so iron's right in the middle of the D block, cobalt's the next element. Cobalt is argon 4s2 3d7, but kind of the same logic. Honestly, I'm just going to reuse the ones from above this. The 4s2 is the only thing not canceling anything out. So even though we added another proton and we added another electron, everything kind of cancels out. So the effective charge is still +2. And the size is 124 picometers. There may be little variations from atom to atom, but the idea is we're moving from left to right across the periodic table, and we're not seeing a trend. It's pretty much flatlining, which is fine. It actually makes life easier. So unlike usually the D block makes things more complicated, this one actually makes it easier. As you go to the right, they don't really change much. So you can almost ignore the effect within the D block. Okay. Let's kind of look at an example of how to actually do something with this. Okay. So let's pick some elements that are near each other. So let's go like nitrogen, oxygen, phosphorus, sulfur. Well, that may actually be the order, I don't know. And when we put them in order from smallest to largest. On quizzes and exams, if I ask you to do this, I will label which side is smallest and which side is largest, because in the past I've had students put it in exactly the wrong order and be like, oh, I meant for largest to be over here. And I have no way of knowing if they know what they're talking about, so yeah. So, the general trend that we saw on the previous page is that things get bigger as you go down and left. So, these things are in a nice little square. Phosphorus is the most down and left. It should be the biggest. And of these four, oxygen is the most up and right, so it should be the smallest. Nitrogen and sulfur are going to be a little weird because they actually kind of are perpendicular to the trend. Okay, so it turns out that the left and right trend is pretty small. Okay, I guess I'll write this here. The left-right trend is small. So in other words, nitrogen is bigger than oxygen, but not by much. Okay. The up and down trend is more noticeable. So what this means for us is if you compared both of these to oxygen, nitrogen and sulfur, that's what we have left to worry about, right? Nitrogen, sulfur. The nitrogen is going to be a little bit bigger than oxygen, but the sulfur should be noticeably bigger than oxygen. So that means the sulfur should be bigger than the nitrogen. The up and down trend tends to have more of an effect. So the sulfur will be bigger, the nitrogen will be smaller. So if we had these four elements, oxygen would be the smallest, then nitrogen, then sulfur, then phosphorus. Okay. So I don't need you to tell me what is the number of picometers across the atom. I need you to tell me, to put things in order from smallest to largest. Okay. We also need to deal with the idea of how does this affect ions. So adding and removing electrons probably has a huge impact on how big things are. Okay, so it turns out that anions, basically negative ions, they are negative because they have extra electrons. What you're doing is increasing the number of electrons without changing the number of protons. So the effective nuclear charge is constant, but the number of electrons has ballooned up. So what we see is that they get significantly larger than the neutral atom. For example, chlorine has a value of 99 picometers. Okay, we don't have a whole lot of reference to know if that's really big or small, but whatever. If you add one electron to that, chlorine is happy to form a negative charge. It'd be like argon, totally the charge we would have predicted. It actually jumps up to 181 picometers. So it almost doubled in size by literally adding one electron. The reasoning is that you're adding more electrons, which is the outermost layers, and you're not increasing the positive charge to pull it in. So essentially, the positive charge that's pulling everything in is kind of getting outdone by the negative charge, and it allows it to expand. Okay. The opposite trend is true for cations. Okay. Cations are the positive ones. And essentially what you're doing is you are decreasing the amount of electrons on the outside, but the effective nuclear charge is essentially staying the same. So the electrons on the outside are not going to, they're going to be pulled in even tighter because there's nothing to counteract this. So how did I phrase it on the anions? So there's going to be significantly smaller than the neutral atom. Because I didn't remember to underline that. Okay, so anions get huge, cations get really, really, really small. So for example, this is going to sound almost the opposite of what we just did. Sodium, if it's neutral, has a value of 186 picometers. That's how big it is. Okay, whatever. Sodium is in column 1. If it loses one electron, it'll be like neon, so we expect it to form a +1 charge. Nothing weird there. Okay, it turns out that its value drops down to about 99 picometers. Okay, kind of almost the exact opposite of what we saw for chlorine. Okay, but literally just removing one electron almost cut it in half. If you have something like magnesium, its value is 160, because we expect things to contract as you go to the right, so magnesium is going to be a little bit smaller. You'll notice it's not a huge difference. Magnesium with a 2+ charge, because that's the expected answer, drops down to 65 picometers. So the effect of charge is more important than the up and down and left and right trend. So in terms of order importance, the charges are the most important factor, then the up and down trend, and then the left and right trend. Okay. Let's try an example and see if we can figure this out. Okay, let's pick something on the positive end, I guess. So let's do sodium, potassium, actually let's do sodium, potassium, and calcium. And then the same thing with the charges. So same atoms, but with their typical expected charges. So this will be 6 of them, and some of these are neutral, some of these have charges. That's okay. So we want to go from smaller to larger. So when you're thinking through this, look at the charges first. The thing that is the smallest is whatever's going to be the most positive, because positive charges make things really small. So no matter where it's at, the up and down, left and right trend, it could be anywhere on the periodic table. Anything that's a +2 is going to be smaller than anything that's a +1. So Ca2 should be the smallest. The next two smallest are the sodium ion and the potassium ion. And the up and down trend, as long as they have the same charge, still works. So things get bigger as you go down, so potassium plus should be bigger than sodium plus. Okay. Now we have the three things that are neutral. So we did the things that are +2, then the things that are +1, and now we have all the things that are neutral. And so from there, we can just look at the typical trend. Things get bigger as you go down and left, so potassium should be the biggest of those three. Okay. And in terms of differences, if we compare them both to potassium, calcium is going to be a little bit smaller because of the effective nuclear charge change, but sodium should be significantly smaller because there's a whole other set of orbitals on top. So sodium should be the smallest, and then calcium, and then potassium. So this is the logic of how to work through these problems. They don't look that bad, but you kind of have to understand the principle of how these trends actually work to be able to figure this stuff out. So the idea is charges are the most important. It's the most important place to start. They have the biggest effect on size. Then the up and down trend, then the left and right trend. On quizzes or exams, I will not give you like, I'm not gonna say like, all right, magnesium 2 plus, gallium 3 plus, molybdenum 4 plus, phosphorus, sulfur 2 minus, like I'm gonna give you things like we've done on these other ones, like things that are close together, things with multiple charges, just to kind of like keep the trend more obvious. Okay, so anyway, thank you.